From the module Electrical Machine 2, we are going to tell you about losses and efficiency in induction motor. I will be talking about efficiency in induction motor, and whereby my friend will be talking about losses in induction motor.
Losses in induction motor. As you all know that in induction motor there will be power losses. So these power losses are classified into two, that are the constant losses and the variable losses. The constant losses are further classified as the core losses and the mechanical losses. And the core losses occurs in stator core and rotor core, and these are also called the iron losses. These losses include the eddy current losses and hysteresis losses, and the eddy current losses are minimized by using laminated construction, while the hysteresis losses are minimized by selecting a high-grade silicon steel as the material for stator and rotor. And as you all know that in rotor, there is a rotor copper losses and the rotor iron losses. The rotor iron losses are very small and hence generally neglected in the running condition. The mechanical losses include the frictional losses at the bearing and windage losses. Now, second, we have the variable losses. This include the copper losses in the stator and rotor winding due to the current flowing in the winding. As current changes, load also changes, and these losses are said to be the variable losses. And this formula is to calculate the rotor copper losses, where I2R means the rotor current per phase at the particular load, and the R2 means the rotor resistance per phase. And to talk about the power flow in induction motor, the power flow in induction motor, the three-phase supply is supplied to the stator, whereby all the power will not be delivered to the stator, right? So there will be a stator losses, and the remaining power will be delivered to the rotor, where there will be a rotor carbon losses and the rotor copper losses and the rotor iron losses, where the rotor iron losses are neglected. And after that, the remaining part of a rotor current is converted into the mechanical, which is also known as the gross mechanical power, PM, that's denoted by PM. And during this mechanical transmission, there is a mechanical losses. And finally, a power is delivered to the load. And these are the losses that occurs when the power flows. Now, moving to the next, my friend Tulasa will be explaining you the efficiency in induction motor.
Thank you. Efficiency of induction motor. In the ratio of net power available at the shaft and the net electrical power input to the motor is called as overall efficiency of an induction motor. The maximum efficiency occurs when variable losses becomes equal to the constant losses. When motor is on no load, current drawn by the motor is small. Hence, efficiency is low. As load increases, current increases, so copper losses also increases. When such variable losses achieve the same value as that of constant losses, efficiency attains its maximum value. If load increases further, variable losses become greater than the constant losses, hence deviating from condition for maximum efficiency. Let's solve one problem. The full load power input to 4-pole 50 Hz 3-phase induction motor is 50 kilowatt, running it 1440 RPM. Calculate its full load efficiency if stator losses are 1000 watt and frictional losses are 650 watt. So let's solve the question. In here, let's write what are given, okay? So in given, it's given that P pole is equal to 4, frequency is 50 Hertz, F frequency is 50 Hertz, PM equals to 50 kilowatt, and equals 1440, and efficiency we have to find, right? So N of S, you can calculate it as 120 F by P. So which is equals to 120 times F is 50 divided by P is 4, which will be equals to 1,500 rpm. So from here, after that, we need to find a slip. So slip is equals to N of S. You know the formula, minus N divided by N of S. So from here, from above we got N of S. So N of S is 1,500, right? Minus 1,440 divided by 0.04. So after getting slip, what we have to find is P2 input. P2 is equals to input power minus data loss. So we know that P2 is equals to P in minus data loss. STAT or loss. So when we calculate this, P in how much is the input power? Sorry, this one is not PM, this is PE. So PE is equals to 50 kilowatt times kilowatt minus stated loss is 1000, which is equals to 49 kilowatt. This is 1000 watt. I can write 1 kilowatt, which is equals to 49 kilowatt. From the relation, we know that P2 by Pm is equals to 1 minus 1 divided by 1 minus x. So from here, we can calculate Pm, which is given as P2 times 1 minus s. So we know that P2 is equals to 49 kilowatt, right? 49 kilowatt. From here, 1 minus, we know that our slip is 0.04. From here, we can get the value of Pm, which is equals to 47,040 watt. So from here, GPM is output. So after that, we need to find P out, output power. P out is equals to Pm minus mechanical loss. Mechanical losses. So from here, we know that our Pm is equals to natural P minus, we know that our mechanical losses is 650 watt. 650 watt. From here, we can get the P out as 46,390 watt. After getting P out, our efficiency will be efficiency is P out by P out divided by P in. So P out is this much, right? Divided by P in. P in we got as this one, 50 kilowatt. Times 5 50 kilowatt, which is equals to efficiency will be equal to 0.9278, which is equals to 92.78%.